Yeah, everybody can see my screen, right?
Correct, yeah.
Okay, cool. Yeah, so I'll be presenting R0, self-evolving reasoning large language models from zero data. So first of all, we started with some motivation for the paper, and the motivation was okay for super intelligence. We want AI systems that can self-evolve. They can learn from their own mistakes. They can generate training data for themselves. And current setup usually have humans generating the initial like training data, the labels for the data that then kickstarts the loop for the agents. And the authors note two problems with the current setup, which is that obviously you have human spending their time hours. You have to hire people to do all of the curation and the labeling tasks. Then we also have the problem of potentially or theoretically, maybe not potentially, the intelligence of the agents might be upper bounded already by the nature of the task that the humans are curating and probably like the model capability itself. So the authors were like, okay, how can we break free from this particular regime, this particular setup? And they proposed a framework where it's a co-evolutionary system in the sense that you have basically two models or two subsystems. One of them is generating the problems, and one of them is attempting to solve the problems being generated. Yeah, so basically the high-level idea is you have a co-evolutionary approach. Again, two models, two agents. One is generating the problem, and one is attempting to solve the proposed problems. Then you have reinforcement learning to basically kickstart a positive feedback loop. So in the paper, the authors named the models a challenger and a solver. So the challenger is proposing problems, then the solver is attempting to solve the proposed problems. So then the rest of the paper is just okay exploring the design of the word function for the challenger, for the solver, and then some ablation analysis, which we are going to get to. So to kickstart, so some basic notes. I will not really be going into GRPO. I think we already like mentioned that almost every paper, or at least almost every other paper is mentioning GRPO or some variant of it. So we'll not be exploring that in this paper, but the almost all of the mentions of RL algorithm would be in reference to GRPO. So yeah, this is basically the high level idea. I'm going to come back to this image towards the end, but let's talk about the challenger. So it's the task of the challenger to generate potential problems to be solved. And then the question is, what sort of questions that are proposed do we want to reward? So the authors note two properties of whatever questions we're proposing is that one, it has to be at the edge of the current solver's capabilities. So the solver can almost not solve this particular problem. And then two, because the challenger would be generating multiple questions at the same time, you want to make sure that they're also diverse. So yeah. So the first requirement, you want to generate problems at the edge of the solver's capabilities. How do you do this? So let's imagine a scenario where we have a challenger, then we sample some problem from the challenger. Then we take a solver, we sample M responses from the solver. We can consider three cases. If the solver solves all of the problems, and this problem is apparently too easy. If it solves none of the problem, this is too difficult. If it solves like a mix, if it solves the problem in mixed ratios, then okay, you can assume that okay, like this, at least according to the authors, this was the notion for a problem being at the edge of the solver's current capabilities. So then the next question is how do you define a reward function for this? And just basically this is the reward function that they defined. And so we'll just sort of walk through walk through both equations, let's say. So you generate a problem from the challenger, the solver generates also like a series of solutions. Then you have a pseudo label. So the important thing to note here is that because there is no external data set at all in this whole setup, all of the problems are coming straight from the challenger. So the only way to like provide the verification signal is through a pseudo label, and in this case, just majority voting. So let's first consider this second equation here. So you have some problem and a solver, and basically the average solve rate of the pseudo label. Then you plug this into this formula here. This is like a little bit hard to read like this. So I sort of plotted this in yeah. So basically this is what the reward function looks like. So sorry, yeah. So this is the average solve rate, and this is the reward for the particular problem solved. And you would observe that basically for problems with zero solve rates or one solve rates, zero reward immediately. Also, more importantly, the challenger is incentivized to generate problems where the solve rate is close to 50%. So basically you have, let's go back here. Exactly. So basically this is what I just showed you, the plot of this thing I just showed now. And the authors term this the uncertainty reward. So again, tying back to what I said earlier, the notion of a problem being at the edge of the solver's current capability is that the solver is the most unsure of the problem. I'm not exactly sure how to think about this theoretically, because it would also seem to me that if the challenger cannot solve the problem at all, then the challenger is also the solver is also not sure of the problem. It's also like uncertain about the problem. So I'm not sure exactly of the intuitions behind this, but I mean, visualizing this reward function sort of makes sense.
I
So
have one question, and maybe you
yeah,
will get. So to get the pseudo
sure.
label for what the correct answer
Yeah,
is, then understand how well the solver solves the problem. Well, where is the majority voting answers are coming from?
right.
Because let's say it's a very hard problem and solver cannot produce any correct solution. So where is the pseudo label is coming from, like what we are measuring against?
Right. So if I get you correctly, you're asking in the case where the solver does not output any response at all, or just output wrong response.
Yeah, so basically in this rightmost side of this reward function where none of the solver's responses is correct, how do we know they're not correct?
Right.
Where the pseudo label is coming from? Because you said pseudo label is coming from the majority voting.
Yes.
Majority voting over which responses?
Yeah. So interesting observation. I had this thought too while I was reading the paper, that potentially you would not have any question with zero solve rates. The worst case you are going to have is every label is diverse, and then it's just like, okay, 1 over m response is generated by the solver. But I don't know, the authors did not mention that. This was also some of the problems, let's say, that I actually had in the paper. Like some things were not very specified in the paper. I'll probably like mention 1 or 2 more of those such things down in the paper. But yeah, basically, I agree with you that you cannot have zero solve rates just based off of this particular setup. I mean, the point is for every problem you're going to have a pseudo label, and then at least the question from which you got the pseudo label will be present in the set. So yeah, the authors do not note anything about that. That'll be my comments.
Okay, but yeah, your note about diversity kind of makes sense.
Yeah.
If there is some set of answers clustered together, we can consider that correct answer, even if the cluster is relatively small to the whole entire set of answers.
Right. Yeah, thank you for the observation.
Sorry, can you go back? Can you go back one slide as well to slide 6? Okay. Is it possible that there are unsolvable questions, or like, I mean, I guess an unsolvable question would have a zero solve rate, right? Anyway, but that's not distinct from just a very hard question, right?
Yeah. So again, I guess like the author's notion of a difficult problem is that like no solve rates according to the authors.
Mm-hmm.
So
Okay.
again, yeah, like that was also part of the reasons why I sought to like plots to be like a better understanding of what the reward function was actually doing. I don't know if I answered your question per se.
No, that makes sense. I mean, all the Ys could be wrong, but all the Ys could be wrong because the problem fundamentally doesn't have a solution, right? That could be possible.
Exactly. Exactly. And yeah, also like there was also some they also enforced formatting on like the way the solver and the challenger were generating the problems. For problems out of format, automatically zero reward. So you do not have such problems, let's say. That was just a side comment. But yeah,
I do
so
have to say this is also a side comment, but this
yeah.
is actually kind of a ripoff of like a very famous paper by Natasha
Mm-hmm.
Jacques at Berkeley. And like she did the same exact thing except in robotics. It's definitely worth checking out.
Right. You
Anyway,
could share the link to the paper probably. It's be interesting to check it out.
sure.
Yeah, thank you. So on the case of diversity, which is second requirement, um, the approach here was also interested. So I would explain the high-level idea, then I would explain my qualms with the approach. So basically, again, you generate a series of problems from the challenger. So we want to maintain diversity among this current batch of generated problems. Then what the authors did was they computed the distance between, so they had a similarity metric between every pair of questions in the set. Then they cluster all the problems together iteratively, all the questions together iteratively. So they had a nice package in NLTK library that did this, but the breakdown of the algorithm was um, in each iteration, you find the two closest clusters. So meaning you have cluster A and cluster B, then the average distance, the average pairwise distance between across all the problems in both clusters. So then you are minimizing this distance. So that's the notion of closest clusters here. Yeah. Then if this distance is less than some threshold, they use 0.5 in the paper. You basically merge the clusters together. So the idea is that, okay, these guys are very similar, so they belong in the same cluster. Then if there are no, like if the distance you get for the closest cluster is greater than the threshold, again 0.5, you end. And the idea is that at this stage, every cluster is far apart from each other, such that the average distance is greater than the threshold of tau. Then the penalty for repetition is basically the size of the cluster. So for questions that belong in big clusters, they get like a bigger penalty, let's say. So I had problems with their own notion of similarity metric, and they were using the BLEU for their notion of similarity metric. This is my first time seeing BLEU being used for similarity metric. As far as I know, it's used for like okay, how similar is some text, some translated or machine translated text to like an human written text. So it was weird to me that they were using BLEU, but they supported this by saying that it's easy to compute this online during the training process. So I mean that was the only justification for using BLE as a similarity metric between two questions basically. But yeah, so we have this then we have the uncertainty reward from previous slides, and then all of them combined into the reward function. So basically, you subtract the repetition penalty from the uncertainty reward function. and then you oh, interesting. You've used VLE for symmetry before. Okay, that's interesting. I'll
It's
take a
not a
look at
big
this.
deal. It's just like it does happen sometimes.
Right, right. Probably you're right then. This is just my first time observing VLE being used as symmetry. But yeah, thank you for that. So yeah, so the final reward function is just basically you are providing a lower bound of 0, but then subtract the repetition penalty from the uncertainty penalty, and then just plug this right into like the GRPO algorithm setup. So basically, again, just to recap the whole thing, you are training the challenger, the solver is frozen, generates a batch of problems from the challenger. For all of the problems, computes the generates a batch of problems from the challenger. The current frozen solver tends to solve this problem. So the solver also generates like M responses each. So compute the average solve rate for each problem. From there, you compute your uncertainty reward. Then you have the repetition penalty as well. So you compute that's the reward function for training the challenger basically. So some notes, I think I already mentioned this earlier, but we have the formats. Yeah. So we have the format tags for the questions being generated by the challenger, and um, yeah, rewards being used for advantage estimation. I think I already said this. So yeah, that's basically all for training the challenger. Then let's talk about training the solver. I'm sorry, my machine is being super slow. I don't know what's wrong. But yeah, so we're training the solver currently. So to train the solver, so again, something I probably did not mention earlier is that um, when training the solver, the challenger is frozen. When training the challenger, the solver is frozen. So you're using like some current copy of the other to train, like you're using the current copy of, let's say, the solver to train the challenger, and the current frozen copy of challenger to train the solver. So to train the solver in this case, um, we again sample a bunch of problems from the challenger. Then the solver attempts to solve the current problems and they filter the problems. So this filtration, um, according to the authors, they do not backpropagate on this first step of filtration. So the challenger generates a batch of problems. The solver generates like another, let's say M solutions per problem. Then using the uncertainty reward that we encountered earlier, so filtering for problems that are too easy or too hard. So they now filter for the solver. So the problems between let's go back to this something. Yeah. So basically the challenger generates a bunch of problems, solver attempts to solve them. And now they're only filtering for problems that had like 60% solve rates. So between maybe that's the wrong way to put it, but basically between 0.3 and 0.7. So either the solver was able to solve it 0.3% of the time or 0.7% of the time. These were the problems that were in the like training set for the current solver. Every other problem was discarded. So now after this, then they now actually carried out the GRPO, which meant sampling again from the solver, using the pseudo labels to generate reward and then carrying out the GRPO. So I don't know how compute intensive the setup is going to be, but it seems to me like it's going to be compute intensive because like you first sample from the solver to do the filtration, then you resample again from the solver. Maybe they have, I don't know what their training code looks like, but maybe they'll be saving like the logits and like the things they need to calculate loss, probably. But like the way they wrote it in the paper, I was just like, okay, they're sampling twice or in 2 rounds from the solver. So, but yeah, basically everything I described is what is on this slide or was meant to be on this slide. So, yeah, sample and responses and all of the nice stuff. So yeah, that's the high level idea. So far, any questions before we continue?
Are they using the same majority voting targets?
Yes. Yes, we are using the same majority voting across both the challenger training and the solver training. So to some experimental configurations, they tested the R0. So what I described now is just the R0 framework. So you iteratively train challenger solver, and yeah. So they tested this on across two model families, but 4 different models. So the Qwen 3 family, and then the OctoThinker. I think OctoThinker was based off of Llama 3.1. So the evaluation scheme is, so you have train challenger, train solver, 1 iteration. You run 3 iterations of this. And it's important to note here that during the evaluation, it is the solver that is being queried to solve the problem, not the challenger. So the challenger's role is just to generate problems. So it's the solver that is actually, let's say, attempting to solve the problem from whatever evaluation suite that is being used. And also another important thing to note here is that, which the authors actually note, that currently the R0 is useful, at least in the paper, they only tried this on math tasks. So basically data sets or domains where the word is easily verifiable. It will be interesting to see how this will be on like code domain. But yeah, they only tried it on math tasks. So again, for evaluation, run for 3 iterations, compare results to the base model, compare results to the base challenger. So this base challenger is in the sense that the challenger, before any training, have it generate some questions, then have the solver solve it, and then that's all they use for evaluation here. And yeah, some more probably relevant metrics is in each iteration, the challenger is generating 8,000 problems. Sorry. Yeah, the challenger is generating 8,000 problems. Then during the actual GRPO training, you have a batch size of 128, and the solver is always generating 10 responses per problem, which is the M metric. So then we go to some results. So the first set of results are this. Yeah. So yeah, the basically almost every paper, like we achieve good results on some interesting benchmark. But it's important to note here that, and again, I think I'm going to allude to this later on, but for most of them, you get the maximum reward at the 3rd iteration. But then it's not every benchmark, it's not every benchmark or every evaluation suite that we had this case for. So there were a lot of cases where, for example, maybe the 2nd iteration or the 1st iteration actually. So for example, AMI 25 for Coin 3 for B base, the maximum reward score picked at the 1st iteration. We also had the case here with 2nd iteration on maths, and basically for other models too. And I'm going to talk about this later on actually. But basically, this was the results for this particular evaluation suite. And again, another set of rewards, same models, just like a different set of data sets. So yeah, but some analysis. So ablation studies. So the authors carried out 3 ablation studies, and the idea was, okay, what is the importance of each of these, all the components of the R0 framework. So they compared first setup, remove the RL training from the challenger. So they are not training the challenger via RL at any step. Second framework, remove all of the filtration process for the solver. So instead of having to filter for 2 easy or 2 hard problems, just train the solver on whatever questions that the challenger generates. And then the third was repetition penalty in the challenger's reward function. And the authors note that removing the RL loop from the challenger had like the biggest drop in performance, average on maths and average in general. But yeah, basically like in the maths data set they tested on average about 4 points drop for the RL challenger compared to like about 2 for just filtering out is too easy or too hard problems for the solver. So they were trying to make the point that the coevolution of the challenger and the solver, and then having RL loops for both of them was actually part of the strength of the R0 framework. So the second point of analysis was they were comparing, okay, so far everything we're describing is you have, let's say, a model Cohen 3 4B base, but it's instantiated as it's instantiated in two copies as both the challenger and the solver. So then they were asking, okay, what if they use the same weights for both challenger and solver? So, and we observe that having the two model R0 framework performed better than the merged or the shared weights. So, and almost across all iterations actually. 48 versus 47, 14 versus 46, 49 versus 45, same as the last iteration as well. So again, proving the point that the two model framework, the two model setup was actually outperforming like just shared weight setup basically. Some other points of analysis is yeah, so this was actually interesting. So basically what they did here in this setup was after training the challenger via RL, sample 200 random problems from the challenger. So again, for each iteration, for each of the three iterations, so you have three data sets. Data set at iteration 1, data set at iteration 2, data set at iteration 3. Now, evaluate the different solvers across the different iterations on all of these three data sets. But now, so now they were not recording only the accuracy, but they were recording the accuracy of the solver using GPT-4o as the oracle. So basically, the solver attempts to solve the problem, generates pseudo label, but they also ask GPT-4o that same problem, and like the accuracy of GPT-4o's answer when compared to the solver's answer. That was what was being recorded. And the claim that they were trying to make here was that the challenger was actually generating more complex questions as the challenger was being trained. So yeah, exactly. So for this, so if you notice like vertically. So the solvers were getting decreasingly, like they were getting decreasing reward for the different data sets. So like the same solver, so solver at iteration 1, you asked it questions generated by challenger at iteration 1, question generated by challenger at iteration 2, and then at iteration 3, and then compare the rewards when compared with GPT-4o. So the takeaway here is that the challenger is actually generating more difficult questions as the training iterations progress. That was the point that this table is trying to make. So also they also compared.
I have a question.
Yeah.
So
Sure.
and maybe that's what you're talking about. So if they use GPT-4o as Oracle, is there like the same vertical comparison of GPT-4o's accuracy across these three sets of problems? So basically,
vertical. I think.
Yeah, go ahead.
I think horizontal. So maybe we are skipping over words here, but let me try to go by it slightly more. So basically, you have the challenger generates problem at iteration 1. Then the GPT-4 solves these problems at iteration 1. Then all of the base models, solver 1, solver 2, solver 3, attempts to solve that same set of problems. And then the accuracy is being compared to GPT-4o. So if GPT-4 generates problems at iteration 1, it is like horizontal across all of different solvers, including the base model as well. I don't know if that makes sense. I think that's the question.
Okay, so this accuracy is relative to GPT-4o answers as Oracle. So basically, GPT-4o is
yes
like for all of this.
Yes.
Got it. Thank you.
Yeah.
And this is F1 relative to GPT-4o's answers?
Yeah, just accuracy, basically.
Accuracy. I mean, those aren't like very high numbers,
Yeah.
right?
Yeah.
Like, I don't know. And it does, I mean, I get it that like if you have this synthetic data, like how are you going to evaluate it? I would expect kind of a human baseline. I mean, what if GPT-4o is getting different categories wrong? Like that wouldn't show up
Right,
in this data. It
right,
doesn't,
right,
yeah.
right. I guess this was also another let's say touch points that I had with the paper where like there were no exact baselines, let's say, but then also how do I put so like the next analysis point I'm actually going to talk about, which is the external labeled data sets. So they were actually using some other like known labeled data sets as a point of comparison actually. So let's just go. So there is the Math12K data sets, GRPO on the base model as baseline. And interestingly, um, so this Math12K data sets, they trained the base model via GRPO on these data sets, then evaluated on the eval suites. So this is the dashed baseline. Then the blue line, they trained the R0 framework 3 iterations. After each iteration, evaluates on the like eval splits of Math12K. So the interesting thing to note here is that R0 alone doesn't actually beat base model GRPO setup. But after a single R0 iteration, you now do additional GRPO again on the solver and then evaluates. So this is the like orange line basically. So the point that the authors were claiming here was that okay, this R0 is like could also be complementary to external labeled data sets, even though like in their setup, the model is generating its own training problems, something like this. So I don't know if this explicitly counts as I mean they never even reference the fact that R0 only like doesn't exceed the baseline. So I don't know if this counts as a point of evaluation per se in itself. But yeah, basically the points that they made here in this section was that okay, R0 is complementary to using running like RL fine-tuning loop on some external labeled data sets. So I think one more point of analysis, yeah. So model collapse. Again, they observed that either the performance gain was observed when evaluating the solver after each iteration, or they actually had like a decline in model performance. And this leads to like actually the next thing I wanted to talk about, which is so I'll talk about the second point first, since it's just like tangential to this. But like I've noticed, again, these are just like personal observations. I've noticed like a lot of papers usually have this theme of okay, RL training. It doesn't just plateaus. You actually have like some kind of model collapse, or and I'm here to like come across any work that actually gave a good explanation, let's say. So the authors here notes that okay, this is probably due to the fact that they were training both the solver and the generate and the challenger on like self-generated data sets. But then this is probably true to some extent. How much we don't know. But my objection would be that across several other works, several other papers, they also demonstrate that RL fine-tuning after some point peaks. So for a good example is like the paper I talked about the last time, start 2. They also mentioned this sort of model collapse. So I don't know, it's quite interesting phenomenon. My sort of rough intuition, I've not run any tests, I've not run any experiments, just like thinking out loud, is that it's probably a combination of the model capacity peaking and then like some something that has to do with the distribution of the data. And this was partly informed by the notes from the authors in RStar2, which I mentioned the last time. But yeah, that's just something interesting. Like even if I open any paper that's RL training, I'm looking for okay, did they mention model collapse? Did they give any good reason for that? So that is that. But to the first thing, while I was reading this paper, the something that occurred to me or it felt that purpose in my head was the framework is similar to training GANs, in the sense that you have two models being trained, and the exact, maybe the difference that's obvious to me is that the error functions are not exactly opposite of each other. So, for example, the challenger being at its best is generating problems that solver is solving 50% of the time, but like is not in any way stopping the solver from also like maximizing accuracy on these problems, let's say. And in GANs, as far as I know, you have this adversarial objective where, okay, the discriminator wants to generate a sample, and its maximal reward is when the generator is generating the sample, and the maximal reward of generator is, okay, the discriminator cannot differentiate if it is like from the generator or from the actual real data set. So my thinking here was, okay, what if we shift the objective function of the challenger? So I was also playing around with this. I mean, again, this is probably nothing, but like just playing around with different things. Like, so it's important to note here actually that, let's come back here. Yeah. So the uncertainty reward function of the generator in this I don't know what to call this function, but in the function that is measuring the accuracy, basically, you have this 1/2 term. So the idea is that this constant is incentivizing the challenger to generate problems that the solver will solve half of the time. So playing around with this particular constant, you shift the peak of the reward distribution curve, if you can call it a curve. So basically, if you change the peak here to 0.2, let me see if I can zoom in. Yeah, exactly. So for the reward function, I define it as you have the accuracy for this problem and then like the peak. So if it shifts the peak to this, basically gets a reward function that looks like this, where the challenger would get maximum reward if the solver can barely solve the problem. But you have these negative reward terms, but then you just like lower bound it by 0, something like this. So like for me, if one of the like probably if I were to continue working on this, one of the things I'll be looking at is, okay, does the peak of the reward function for the challenger have any effect on, let's say, increasing, I don't know, the general capabilities of how much the server can solve? Do we get further model collapse by, like, I don't know, making the challenger generate more problems? Though my objection to this would be that it's busy to reward arc this particular reward function. But yeah, I don't know. These are just my rough thoughts about the paper. So these were my two observations. So yeah, thank you. If anybody has got questions or comments.
Yeah, thanks, Israel. Thanks. That was a really nice paper, and a really nice presentation. I really like that you like scoped out different parts and were kind of giving us good visuals to kind of understand the reward functions and stuff like that. Yeah, I mean, it's an interesting paper. I am also very curious, like whether they did evaluation or at least like qualitative evaluation of the questions that were being generated. Like, it would be really cool to show in the appendix like samples of the kinds of math questions that were being generated and then getting harder and harder. I'm also like curious. I'm also curious, like nothing that you mentioned, there's no limits on it staying in math. So because they're enforcing diversity, because they're getting harder and harder, they might also be kind of generalizing their problem space beyond math. So yeah, I guess those are my two questions. Like, did they give examples? First of all, and then second of all, uh, did they observe any drift happening, or is it were there things that like were preventing this drift?
Yeah. So to the oh shoot, sorry. Yeah. So to the second question, I guess two points of notes. First point is for this particular setup, the prompt was basically like telling the challenger, okay, you are some sort of maths professor, something like this, generates maths problems specifically. So they did not note if the nature of the problem drifted out of maths domain during the course of training. So I would want to guess that the challenger stayed on point, but then again, like you would have to observe the data. If there's anything from RL general I've learned, you want to observe data before you make such strong claims. But yeah, my first rebuttal to that would be that the authors made the point that the prompt was okay, generate this number of math problems, something like that. Second point, still on that particular question, is that it seems to me that again, sort of agreeing with the authors, this only works in verifiable domains. Verifiable in the sense that you can easily compare answers. So, for example, for a math problem with like some sort of numerical answer, it's easy to get okay. At this, you can do some sort of like string matching, something like this. Code is slightly I mean almost the same thing as well. You run like the code, do you get the same outputs or the same sort of unit test pass? So I would assume again for verifiable domains, this is easy to do some sort of the only objection I have is, for example, and I was thinking about this actually, that if I were to run this on code domain, what would I have to do? The problem is sort of like the challenger would have to also generate unit tests that would be used to evaluate the whatever code blocks that the solver proposes. Or maybe they're having code questions where it is only just like competitive programming style problems where you have like question, then some sort of test case that you can evaluate to get some specific answer. So that's a separate regime. But if it's just like, okay, you have to implement a function or you have to like fix some bug, as far as I know, the only way to verify this is you're comparing unit tests that pass or fail before and after you apply the patch. So this might be exactly challenging in for this particular setup. But if it's just restricted to questions where, okay, you have some sort of again, programming competition style problems, run test case, get your answer, it's easy to verify. That being said, the second point of note is if they add examples of questions here in the appendix. So if I'm being honest, I did not exactly go through them, so I can't like give you an informed point of view. But yeah, I mean, for them to have included it, it must have been. Also, they did not give any specific comments to the coherence of the question, like as the situation progressed. So they just said, okay, they just noted in the appendix that okay, these were examples of questions that were generated by the challenger, something like this. But they did not say, okay, we got probably like the coherence of the questions got worse as the iteration declined. They did not make any such notes. I don't know if that answers the question, I guess.
Yeah. No, I'm scanning this paper. I mean, definitely were they to submit this to a conference, they'd probably get like some pretty heavy pushback for like the lack of human evaluation and the lack of
Right,
examples and stuff like that. But it's still,
right.
I still think it's a cool idea, and they do have some nice experiments and explorations.
Yeah, 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 yeah.
One question I have in in the GRPO baseline,
So
which they fail to surpass with just R0. Do they mention how they train this GRPO baseline? Do they use external Oracle of some true verifiable rewards, or
yeah, so yes, so yeah, yeah. So for this GRPO baseline, for the base model, for the baseline, they use the Max 12K dataset. So the Max 12K dataset has both train suites and eval suites. So for the baseline, without the R0 in it, you train on the train suites, evaluate on the eval suites. For every other setup, all of the training data was generated by the R0. So the eval was on the eval splits of the Max 12K. So that means during the trading process too, all of the pseudo labels were from like majority voting from the solver.
okay, that makes it more
Yeah,
defensible, I think, even though they don't really surpass the baseline with R0 only, given the fact that R0 is only trained on synthetic problems and pseudo labels. It's still
yeah,
interesting.
yeah.
I have a question. The STAR papers, the self-taught
Sure.
reasoners, often use GRPL.
Yes.
And for their verifier model, they evolve the reward function. So like you were saying at the end there, changing the reward function. So I believe what they do is they just evolve it. So at each iteration, they, well, yeah, so if it's 30%, then they'll make it, yeah, now it can do 30%. So that they'll just keep on changing that function such that yeah,
Right.
the problem set is always generating 50%. So not necessarily evolving that one or fine-tuning that one. Don't you think that that would be a similar result in a similar improvement?
Oh,
Does that make sense?
I'm not exactly sure I understand actually. Because
So
as far as
yeah,
I
they
know,
kept it at
in this,
50%,
yeah,
right? And they evolved it. But instead, each iteration go from 50% to 30% to 10%. Just evolve the reward function as opposed to actually fine-tuning the challenger model.
oh, interesting. Okay, yeah.
Yeah, that's interesting. So like, yeah, just make it
I
more challenging.
yes, exactly. I didn't think of this actually. It's interesting to see. I guess I don't have any like informed answer for that. That's surprising insight.
Mhm.
Ah, okay. I mean, I would see why that would make sense to do. You basically want to make it you want to like re make the problems more challenging that the challenger is generating. So in theory, I would see why that would make sense. But then again, empirically, it would be interesting to observe how this is going to be, especially with the solver. So something actually did not mention in this data set here is that like if you look across this diagonal, yeah, exactly on this page actually. Okay, I think I need to stop expanding the page. But basically, if you look across the diagonal, the accuracy of the solve rate was approaching 50%. Yeah, so um the 59 here, 51.5 here, 50.5 here. So like the model was also trying, the authors were trying to make the point that okay, yeah, like the server's capability was actually approaching the ideal range, let's say, for the challenger. So also my thoughts when thinking of okay, shifting the reward design by a bit was okay, it would be interesting also to observe how that changes. I mean, if the solver is solving like 10%, I would want to be worried that okay, it's something going on. But then if the challenger is generating problems and the solver is solving 10%, you want to assume that okay, the challenger is doing something right. So yeah, I guess that would make sense. But again, I would want to observe how that evolves with the solver's solve rate, let's say.
Mhm.
Yeah.
Yeah, there's a few things I guess directions you could take this.
Yes, exactly. I mean, like even in so my probably just some closing thoughts. Like some of the details in the paper were very underspecified, very underspecified. I mean, we already talked about some earlier. I remember one now. They had a column. They had a column in the paper where they were talking about how the fact. So they were basically trying to measure the pseudo labels, the accuracy of the pseudo labels across different iterations. But then they did not mention which solver was generating this particular pseudo label. Like from which solver do you get the pseudo label? They didn't mention that. So it was I was trying to understand. Okay, this doesn't make sense just in isolation. There has to be a solver, but then like the detail wasn't present. So I guess there were a couple of problems are generally with the paper, but like the idea in spirit, the idea makes sense. I mean, it's something that I think if gotten right, or again for verifiable domains could really scale things up. So yeah, and also like there are still like I feel, a bunch of experiments that could be run to further like ground the results of the paper overall.